The next speaker is Dr. Jennifer Beck from the University of Toronto, Sunnybrook Hospital and St. Michael's Hospital, and she'll be presenting work on the concept of NAVA.
Mr. Chairman, ladies and gentlemen, and McKay, thank you very much for giving me the privilege today to talk to you about improved synchrony and respiratory unloading by neurally adjusted ventilatory assist, or what we refer to as NAVA. And I'm going to start the presentation by showing you several different types of patient ventilator asynchrony that can happen, and it's a little bit repetitive from what Art and Laurent were showing. I'm also going to use the beautiful slide of Martin Tobin that was published in the New England Journal of Medicine, and it describes the classical interpretation of asynchrony, where we talk about a mismatch in timing between the patient's neural inspiratory efforts and the ventilator-delivered breaths. Art went through the slide. It has flow and airway pressure. Sorry.
Okay.
Sorry. This is the diaphragm electrical activation, and this is the electrical activation of an expiratory muscle. This is in a COPD patient breathing on pressure support. So you can see here that there is a significant delay between the onset of the neural inspiration and the onset of the ventilator in the range of 800 milliseconds on this slide. But also important, like Art pointed out, there's actually a delay between when the EMG signal stops and the ventilator continuing to deliver assist. So you can see here, when you compare the patient's neural inspiration with the ventilator delivered timings, you can see that the overlap period is very short. Now, besides timing, there's another extreme form of asynchrony, which Laurent also went over. These tracings are obtained from a paper published in Nature by Cinderby. It shows the diaphragm electrical activation. So here you have each neural inspiratory effort and the airway pressure taken from, again, a COPD patient breathing on pressure support ventilation with a conventional airway pressure trigger. And you can see here very nicely that again, we have problems with timing, but also you have these wasted efforts where there's a clear neural inspiratory effort made by the patient and the ventilator was not triggered. I'm going to introduce to you now another type of asynchrony that a lot of people aren't aware about. So besides the timing issues, the wasted efforts, you also have asynchrony when you have changes in respiratory drive and the ventilator does not respond. These data are taken from a colleague of ours in Montreal who is studying diaphragm activation during different modes of ventilation. We have flow, volume, and airway pressure. It's a COPD patient. And you can see that things look okay. Now, when I show you what the diaphragm electrical activity is doing, you can see that there's actually quite a variation in the respiratory drive in this patient. In one breath, you can have a high level of diaphragm activation and receive a certain amount of assist. In another breath, you can have a very low diaphragm activation and still receive the same amount of assist. And again, also, you'll notice that for the same electrical activation, this breath was triggered, but this one was not. So what I've shown you is that these are just 3 isolated examples of patient ventilator asynchrony. And the question that I get most of the time is, how often does this occur in the ICU? And Laurent is nicely presented to us about the wasted efforts. But in a general population in the ICU, how bad is the asynchrony? We did a study a few years ago where we monitored the diaphragm electrical activity in a general population of ICU patients. They were on different pressure support levels, they were on different ventilators, and they all had diseases, acute respiratory failure of varying etiology. What I'm going to show you now is group mean data for neural timings of these patients and the ventilator timings. The black solid line represents the diaphragm electrical activity. Again, this is for a group of 13 patients with acute respiratory failure. So this is inspiration, this is the end of neural inspiration, this is neural expiration, this is the next breath. The green line demonstrates the volume that was delivered by the ventilator, and the red line demonstrates the pressure support level. In this case, it was 20 centimeters of water. And you can see, like I showed you on the Tobin slide, that there are significant delays between the onset of the diaphragm electrical activity and the onset of the assist. That's the trigger delay here. You also see that there is a period where the ventilator continues to deliver the pressure support after the neural inspiration has ceased. And I'm going to give you a little bit of numbers now to take home with you. If you look at this delay, you see that it's approximately 30% of the neural inspiration. So the patient is actually, for 1/3 of his neural inspirations, trying to trigger the ventilator. As well, during the neural expiratory period, you see that the patient is receiving assist. Again, 1/3 of his neural expiration is spent receiving assist when he does not want it. And you may say, oh yes, this is a very high pressure support level, and we can anticipate this asynchrony. When we reduce the pressure support to a level of 2, almost nothing, we found that the diaphragm activation doubled. However, the phenomena of trigger delays and overinflation were still present. And as the previous speakers have also mentioned, is that patient-ventilator asynchrony is complex, and there are a multitude of factors that contribute to it. And I'm not going to go through all of these. There are a lot of papers published on the topic. I will, however, maybe focus a little bit on the level of the assist and how it contributes to asynchrony, and how leaks can contribute to asynchrony. Generally speaking, if patient-ventilator asynchrony becomes very severe, we often have to resort to suppressing the patient's respiratory drive, and we have to sedate and sometimes even paralyze the patient. And as Theo expressed, can have negative consequences to the muscles and may even delay a weaning process. If you do not cycle off the ventilator and continue to deliver assist, there is a potential for lung injury. And this has been shown in small children that if you have expiratory asynchrony, you can get pneumothoraces. And another negative consequence of patient-ventilator asynchrony is that we believe it is one of the major contributors for the failure of implementing non-invasive ventilation. So I think from all the talks we've seen that there is definitely a need to improve patient-ventilator interaction. So how do we improve the synchrony? We have to go back to the physiology for a second. The desire to breathe originates in the respiratory centers. The signal from the respiratory centers is passed to the phrenic nerve. This signal electrically activates the diaphragm. After the electrical activation, the diaphragm contracts. This causes changes in pressure. It displaces the chest wall, and it generates an airway pressure, a flow, and a volume. It is these signals, these pneumatic signals, that are today used to control the mechanical ventilator. However, you can imagine that, especially in disease, the original signal from the respiratory centers can be filtered, delayed, dampened, and transformed by the time it gets down through the whole chain of events. Ideally, we would like to control the ventilator directly from the patient's respiratory centers, but this is not feasible. The phrenic nerve has been used to control a ventilator in the early 70s, but this has only been implemented in animal models. The diaphragm electrical activation is the signal which is the closest signal to the respiratory centers that can be measured in humans. And it is this signal that we use to control the ventilator, and that I'm going to present to you some data that we have about this today. This is a schematic of the setup that we use to neurally control the diaphragm. We measure the diaphragm electrical activation with an array of electrodes which are mounted on a conventional nasogastric feeding tube. Here you have a blow-up of the signals as they come out from this electrode array. Once we measure our signals, they are fed to a PC where they are processed, and the processed signal can be monitored or can be sent to the ventilator to control it, to deliver the assist back to the patient. This is neurally adjusted ventilation. It is a mode which is a partial ventilatory assist mode, where the airway pressure is delivered in proportion to the electrical activity of the diaphragm. So this is one inspiration here. With the prototype of NAVA that we're using today, we are actually triggering the assist when the diaphragm electrical activity begins to increase. We are delivering the assist proportionally and instantaneously every 16 milliseconds until the diaphragm electrical activity begins to go down, and then we are actually cycling off the assist. With NAVA, the assist is equal to the diaphragm electrical activation times a gain factor. So if your gain factor is 1, you simply have that the assist is directly proportional to the diaphragm activity, as you see here. However, if you would like to increase the assist in this patient, either they have to increase their diaphragm electrical activity and then they will get more assist, or you can increase the gain, and that means that you multiply this signal times a number and then you get a new level of assist. And I think that will become more clear on this slide here. On the x-axis, you have your diaphragm electrical activity in arbitrary units, and you have airway pressure in centimeters of water. This can schematically be thought of as one inspiration from 0 to 10 arbitrary units. And with a NAVA gain of 1, you would get 10 centimeters of water. If we increase the gain by 2, for the same amount of electrical activity, so 10 units of electrical activity, you get twice the amount of assist. And again, if you increase the NAVA gain to 5, again, for the same amount of diaphragm electrical activation, you would increase the assist by 5 times. Here's an example of NAVA implemented in a 2-kilogram rabbit who has an acute lung injury. We have on the top tracing the diaphragm electrical activity, so each one of these black triangles represents an inspiratory effort. And on the bottom, you have the airway pressure when the NAVA gain was set to 1. So we have a direct proportionality between the diaphragm activity and the airway pressure. When you increase the NAVA gain tenfold, these are the results. You get a reduction in the respiratory drive by about 2/3, and you can see here the assist that was provided. And the reason why you don't see a tenfold increase in the assist, because we could imagine if this could be 10 times as high, is that the response of the animal to the increase in the assist was to deactivate, and therefore you get a proportional increase in the assist with a proportional deactivation of the diaphragm. An interesting thing is that, in relation to Theo's talk, is that you can increase NAVA gain, but you will always have maintained synchrony, and inherent to the mode of NAVA, you will always have some degree of diaphragm activation in this mode. Now let's look at what happens during pressure support in the same animal model. Again, we have a rabbit with an acute lung injury, the diaphragm electrical activity signals on the top, and the airway pressure on the bottom when pressure support was 4. And things look okay. If we wanted to unload this rabbit, however, when we increased the pressure support level to 12, what we found was there was an increasing amount of wasted inspiratory efforts. And this was associated with an increase in the diaphragm electrical activation, as well as an increase in the pressure time product of the diaphragm for when you calculated the pressure time product for both the effective triggering efforts and the wasted efforts. So you can see that when you have synchrony with NAVA and you increase the level of the assist, as I showed you in the previous slide, we had unloading of the diaphragm with maintained synchrony. However, when you have asynchrony, you may in fact actually load the diaphragm during increasing assist with pressure support ventilation. Now, what about non-invasive ventilation? Here you have a healthy subject breathing on NAVA. This is the esophageal catheter that she has. It's recording her diaphragm electrical signals. The signals are being processed. They're being fed, to the PC. They're being processed. The controller signal is then fed to the ventilator, and the ventilator is responding by providing the assist to this lung model here. Please don't pay attention to these Respiratory bands. They're part of another protocol. But I want you to pay attention to, first of all, here we have 100% leak. There's no interface between the patient and the ventilator in any way. It's all being neurally controlled. So you can see here that the lung model is responding to the depth of her breathing as well as her rate. And the point I wanted to make with this short video clip is that NAVA is a pneumatically independent mode. It is neurally controlled, and therefore it is not affected by leaks. And this opens up a whole new field and possibilities for non-invasive ventilation. And this is the work we're doing right now. We're looking at non-invasive NAVA in a very sick animal model of acute lung injury. I have to describe to you a little bit the model before I show you the slides. We have our rabbits. First, we have to orally intubate them so that we can perform the lung injury. After the lung injury, and we have our diaphragm we have our diaphragm EMG catheter measuring the electrical activity of the diaphragm. After we perform the lung injury, we pull the oral endotracheal tube and we insert a small nasal prong into one nostril of the rabbit. So it's a very small catheter that goes in the rabbit where we're going to ventilate him with NAVA. And I want you to remember, first of all, these animals are very sick. The PF ratio is about 130 and their compliance is reduced to about half. But also importantly is that there's leaks around the nostril where the tube is inserted. There's leaks from the other nostril and there's leaks from the mouth. Now I'll show you the signals that we obtained. Of course, if you try to do pressure support ventilation with this kind of a setup and you have a pressure trigger, the ventilator cannot detect changes in the pressure because the leaks are too big. So you see here that the animal is making significant inspiratory efforts. There is no assist delivered, and there is a fair amount of esophageal pressure swings. And what we did was we also tried to go to a flow trigger and found that it was just auto-cycling and hanging up all the time. Then we put NAVA, and you see that we were able to restore the assist. We were able to reduce the work of the breathing, the esophageal pressure swings were reduced, and the diaphragm activation as well went down. And you see we're always maintaining synchrony in terms of timing in both as well as the drive. Here you have small breaths and here you have big breaths. The blood gases after a few minutes on this mode showed respiratory failure. Upon implementation of NAVA, we were able to restore the blood gases in this animal. This slide is just to show you, again, in the same experiments, how you can actually even not only have synchrony, but you can also unload the diaphragm. So you have here the same animal model, you have their diaphragm activation, your airway pressure with a low NAVA gain, and then when we increase the NAVA gain, you have a reduction in your diaphragm activation, and the assist went up proportionally. Again, with maintained synchrony and maintained activation of the diaphragm. This is almost my last slide, and it's basically the visual image I would like you to take home from this talk. This is data that we now have, again, from my colleague in Montreal who is comparing pressure support to NAVA in intubated adult ICU patients. And on the left, you have pressure support with the 3 examples of asynchrony I described to you earlier, where you have varying respiratory drive, pressure support doesn't respond, wasted efforts, and delays. So you have here a neural inspiration, and the ventilator is still delivering the assist. And all we did here was we flicked a switch. We have a controller switch, so we went from pressure support to NAVA just by changing one button. And as you can see here, we were able to immediately restore the synchrony of this patient. And this is the summary of my talk. At patient-ventilator asynchrony does occur, and I'm not the only one to show it. It was also presented by the previous speakers, and if severe, may cause respiratory loading. However, improving patient ventilator synchrony offers efficient respiratory unloading, as I showed you with the NAVA slides. And this is what I think is the most exciting work right now, is that NAVA delivered non-invasively is able to unload the respiratory muscles and to provide adequate ventilation. Thank you.